Section 1.4 looks at graphs of functions in a few different pieces. So the first is finding a domain and a range. So this is our first topic here. And a domain, if you are familiar with this or have heard of this before, these are all of our x values, and the range is all of our y values. So if you look at the picture on the left, we're talking about a closed interval here. There's no arrows on the end of this graph. So our domain is going to be from one x value to another, and our range will be from one x value to another. So we can write it in a few different notation types. I'm going to show you two. So the first one, I'm going to write it in brackets, and I'm going to say the x's, you can see here they have a nice picture drawn for us. Our x's on our domain go from, they tell us that it's -1. I shouldn't have not here. They tell us it's -1 to 4. So I'm going to go from -1, the x falls somewhere between there and 4. And then I need to look at the type of circle on the point. So since the 1 is a closed circle, I know that it's included. Refresher on inequality symbols. And since the 4 is an open circle, I know that it's not included, so it does not have the line under it. I can write it like that, or I can write it like this, a square bracket with a -1, and then the 4 with a rounded bracket. So for our range, we're talking about our y values, and so we're going from, they tell us that our lowest y value is -5, and our highest y value is 4. So I'm going to be looking at, oh boy, sorry, -5, and then the y is in between here, and then it goes up to 4. I have to look at the circles. At the places where we're talking about the highest and lowest y, our circles are both closed. They're both going to be less than or equal to, or greater than or equal to. And then over here, I would write it as -5 with a square bracket and 4 with a square bracket as well. To determine the domain of a function algebraically, you need prior knowledge about the graph. So if I didn't have a picture of the graph, I would either have to graph it or put it in a calculator and look at it. If I don't have that, I'm going to have to use my prior knowledge. So if I said algebraically find the domain of the function f of x is equal to the square root of x plus 4, I would need to know the square root looks something like this, the parent function. Or I need to know that I can't have values that are less than -4 in there. If I put -4 into that function, -4 plus 4 is 0, square root of 0 is 0. If I put -5 in there, I'm going to have -5 plus 4 is -1. As far as we know, you can't take the square root of a negative number. You can actually, but it's an imaginary number. We're not going to deal with that until later. So we would have to say the domain would have to be, oh my gosh, x values such that, that bar means such that, x is greater than or equal to -4, right? It could be -4, it'll just be 0, but any number smaller than -4 isn't going to work. And if you left out 4, you would technically be wrong. 4 would work in there. So you need the greater than or equal to. Okay, the next thing up is increasing and decreasing functions. It might not be a bad idea to pause the video at this point and just copy down the notes. It's very wordy. And so I'm going to explain, we're going to read the formal definitions, and I'm just going to explain it's a lot easier than it looks. So a function is increasing on an interval for x1 and x2 in the interval where x1 is less than x2, meaning I picked a number on the left for the first one, a number on the right. It's getting bigger as I go across from left to right. And that implies that f of x1, meaning the y value associated with x1, is less than the y value associated with x2. All that it's saying is as I go from left to right, the function is going up. The y value is going up. This y value is smaller than this y value, and that x1 value is less than this x2 value. So you can probably take a guess what a function looks like when it's decreasing, or what it means when a function is decreasing. For any interval from x1 to x2, where x1 is less than x2, it's saying that the y value of x1 is going to be bigger than the y value of x2. So the function is going down as you go from left to right. Okay, and then our last bullet, a function is constant on an interval for x1 and x2 when the y values are the same. So this right here, constant, we would say this line right here has a slope of 0. You have to think back to 1.1 or back to your Algebra 1 days. That has a zero slope, okay? Another way to think about it is if you were on a roller coaster and you were on the ride of the function at hand, right? If you were on a drop, it would be decreasing. When you're just going straight, it's constant. If you were going uphill, increasing in your height, it'd be click, 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 right? The chain's taking you up the hill. That's increasing. So, but you must be going from left to right. So if you're dropping as you go from left to right, the function is decreasing. It's constant when nothing's happening, and then it's increasing as you go up. So we look at this function here, f of x is equal to x to the third minus 3x. Is this function increasing or decreasing? Well, that's a trick question here because it's doing a little bit of both, right? At this point, if you were on a roller coaster, it'd be increasing, you'd be going up. Then we get to this middle section where you would be dropping, it'd be a decrease, and then you get back to this increasing section. So we write it like this. I'd write increasing, and I'm going to write the intervals where it's increasing. And I only write the x values. So I don't care about the y's, I don't care how high it's going, I don't care the height of the hill as I'm on the roller coaster. All I care are the x values, okay? So note here, because this seems to be a common issue, only use x values. This is an example of something you want to put in your notes even though it's not already in the type part, okay? So increasing, if I'm coming from this direction, I'm assuming the function looks like this. It's not stopping, it's not a closed interval, it's an open function. There's an arrow here. All the way on this side would be negative infinity. So from negative infinity to -1, I'm increasing, I'm going up. So from negative infinity to -1, I'm going up, okay? On the right, I can't put a square bracket on infinity, doesn't exist. And then at -1, that's a special point. So technically I'm not increasing at -1 anymore. So I'm going to leave that out. And then I'm also increasing. I put a comma, open another set of parentheses, another interval. I'm increasing from 1 to, if I'm going all the way this way, I'm going to be approaching infinity, positive infinity. So I write 1 to infinity. That tells me that I'm decreasing in that middle section, which we highlighted in green. So I'm decreasing from -1 to 1. From this chunk of the graph, I was decreasing. Okay, these points, like I said, the turning points where you'd be at the top of the hill waiting before you fall down, but you're not clicking anymore. There's like those few seconds where let it sink in. Those are special points that we're going to talk about in the next piece, okay? So they're not included. So increasing, we only deal with the x values. Same thing for decreasing. I only care about the x values. Notice I'm not writing any of the y values. I didn't even look. I don't care what the y values are. I just care about where my x's are when I'm increasing or decreasing. Okay, so those special points are called the relative minimum and maximum values. So the points where the function changes from increasing to decreasing, those hang in the air points, that's your maximum or your minimum values of your function. Function is called, or the function value is called a relative minima of f when there exists an interval such that f of a is the smallest thing compared to f of b, so the lowest y value, okay? So for these, we are talking x and y values as opposed to just the x's. The function value is called a relative maxima of x when there exists an interval such that f of c is greater than f of d. So again, that's the wordy definition, but here's what you're really saying. A max, they tell you, they have it written in here nicely for you, is the highest point. It's a peak. It'd be a hill in a roller coaster, right? This is a max. And then this right here is also a max. It's a peak, it's a top, it's where you go up and then go back down. So that tells me that my minimum values, if I could call, you'll be able to see a little better, are where it bottoms out and turns around. So minimum values bottom out and turn around. I'm going to refer to them as mins and maxes as opposed to a relative minima and a relative maxima. Notice it's not the ultimate max and min. That's why we say relative. When people say it's all relative compared to the things around it, okay? So in this part of the function, yeah, this is the highest piece right here. In this part of the function, this is the lowest piece right here. That's the relative max and the relative min. But this function goes on. So its actual max is going to be infinity. And if it keeps going this direction, its actual minimum is going to be negative infinity. So it's relatively speaking, it's the relative max and the relative min. In order to find those values, you really need a graphing calculator. We are not going to spend time doing it all by hand. We'll look at other ways to come up with them and figure out what those points are and how we can graph them. Our next piece is a piecewise function. So 1.3, we looked at how to evaluate a piecewise function. Now we're going to look at how to graph one. So when you're sketching a graph of a piecewise function, if you remember, a piecewise function is two functions that are smashed together. So I'm going to need two XY charts. So I'm going to do an XY chart up here, and X, Y. I'm going to put my first function. You can have more than two functions. You can have multiple pieces of your piecewise. So I'm going to do that, and I'm going to do it in blue, and then I'll do the next piece in pink. And I'm going to look at what I'm going to put in for my X values. I have to decide. So in the blue, I see that it's X is less than or equal to 1. Here's the thing. I want to put my benchmark 1 in this value. In this case, it is a 1, my benchmark value in both. So I notice there's a 1 in this function and there's a 1 in this function. That's the overlap. That's where the function switches over. That needs to show up in both of my XY charts. So here I'm going to put it here because that's the highest X value we're going to get. Here I'm going to put it here. It's the lowest X value I'm going to get. So that needs to show up in both. That's an important thing you want to write down and make note of. That value that shows up in both, that changeover point, needs to show up or you're going to be missing chunks of your graph. Okay, I'm going to look at X values that are less than or equal to 1. So I put 1, 0, -1. I can put an arrow on the end and continue. And then the other part of the graph only goes up to 3. So I'm going to do 1, 2, and 3. Even though it says less than 3, I'm still going to do 3. And then I'm going to use my open and closed circle knowledge to come up with how I'm going to sketch this graph. So I need to plug the pieces in. I'll give you a few minutes to do that. So it might not be a bad idea to pause your video and write them all in because in a second I'm going to pause the video, do all the work, and then come back to a completed screen. Okay, all I did here was substitute in the X values I came up with to come up with corresponding Y values to get my coordinate pairs, and now I'm going to graph them. So I'm going to start with the top function, which was when X is less than or equal to 1. So at -1, I found that the Y value was 1. I'm going by ones on my graph. I didn't write in any of the values just so that it's a little easier to see. So at -1, I'm talking about 1. At 0, I'm looking at 3. 1, 2, 3. At 1, I'm looking at 5. 3, 4, 5. If you notice up here, I have a equal to inequality, so I include the 1 by using a closed circle. Now I would take this and continue the function beyond, right? This function keeps going. X just stops at X. So I take this and I just draw any sort of straight line I can come up with here through those points, and that's half of my function, okay? Because the other half, which I'm going to do in pink, is going to be at 1. I'm going to go to 3. But if you look here, I have an open circle on both of those. Okay, I shouldn't have done that. Open circle, open circle. So at 1, I'm looking at the point 1, 3. I go to 1 up to 3, and I just draw a circle there. And then I have the point 2, 2, which is included. So I'm going to draw a full circle, 2, 2. And then at 3, 1, again, an open circle. So open circle at 3, 1. I'm going to draw a line to connect those 3 dots. And that's actually my function. It looks a little weird, but that's how a piecewise function works. There's multiple pieces crunched together. If we had another example and there was something on here about another function that picked up at 3, so 3 was included here, we would just draw on the next part of our function wherever it picked up, something like that, right? It would continue on. So you can have multiple pieces, you can have multiple functions, but you just break it into separate XY charts, and this is what you really want to look at. You really have to be careful looking at, this is your key basically. It's telling you what to put for what XY chart, and then that tells you also whether you're using open circles or closed circles. So again, here are your steps. Determine each domain, create the tables, and then graph each piece of the function. We're going to hit even or odd functions in class because we're going to look at what an even and odd functions are, and then also how we determine if functions are even or odd.